An antimatter weapon is a hypothetical device using antimatter as a power source, a propellant, or an explosive for a weapon. Antimatter weapons are not thought to currently exist due to the cost of production and the limited technology available to produce and contain antimatter in sufficient quantities for it to be a useful weapon. The United States Air Force, however, has been interested in military uses, including destructive applications, of antimatter since the Cold War, when it began funding antimatter-related physics research. The primary theoretical advantage of such a weapon is that antimatter and matter collisions convert and produce a greater fraction of the weapon's mass into explosive energy when compared to a hydrogen fusion reaction, which is only on the order of 0.4%. The basic equation governing the antimatter reaction is Einstein's famous E=mc², but since a given mass of antimatter needs an equal mass of ordinary matter with which to react, this effectively becomes E=2mc². Therefore, a gram of antimatter would need a gram of ordinary matter to release its energy, and the energy developed would be 2*1 e⁻³ equals 1.8 e⁻14 joules. Using the convention that 1 kiloton TNT equivalent equals 4.184 e⁻12 joules, the gram of antimatter reacting with its ordinary matter counterpart gives 43 kilotons of explosive force. Acquiring and storing antimatter. Antimatter production and containment are major obstacles to the creation of antimatter weapons. Quantities measured in grams will be required to achieve destructive effect comparable with conventional nuclear weapons. 1 gram of antimatter, annihilating with 1 gram of matter, produces 180 terajoules, the equivalent of 42.96 kilotons of TNT. In reality, however, most known technologies for producing antimatter involve particle accelerators, and they are currently still highly inefficient and expensive. The production rate per year is only 1 to 10 nanograms. In 2008, the annual production of antiprotons at the Antiproton Decelerator facility of CERN was several picograms at a cost of $20 million. Thus, at the current level of production, an equivalent of a 10-mount hydrogen bomb, about 250 grams of antimatter will take 2.5 billion years of the energy production of the entire Earth to produce. A milligram of antimatter will take 100,000 times the annual production rate to produce. It will take billions of years for the current production rate to make an equivalent of current typical hydrogen bombs. For example, an equivalent of the Hiroshima atomic bomb will take half a gram of antimatter, but will take CERN 2 million years to produce at the current production rate. Since the first creation of artificial antiprotons in 1955, production rates increased nearly geometrically until the mid-1980s. A significant advancement was made recently as a single anti-hydrogen atom was produced suspended in a magnetic field. Physical laws such as the small cross-section of antiproton production in high-energy nuclear collisions make it difficult and perhaps impossible to drastically improve the production efficiency of antimatter. Research conducted in 2008 dramatically increased the quantity of positrons that can be produced artificially. Physicists at the Lawrence Livermore National Laboratory in California used a short, ultra-intense laser to irradiate a millimeter-thick gold target which produced more than 100 billion positrons. Even if it were possible to convert energy directly into particle-antiparticle pairs without any loss, a large-scale power plant generating 2,000 MWe would take 25 hours to produce just 1 gram of antimatter. Given the average price of electric power of around $50 per megawatt-hour, this puts a lower limit on the cost of antimatter at $2.5 million per gram. They suggest that this would make antimatter very cost-effective as a rocket fuel, as just 1 milligram would be enough to send a probe to Pluto and back in a year, a mission that would be completely unaffordable with conventional fuels. By way of comparison, the cost of the Manhattan Project is estimated at $23 billion in 2007 prices. Most scientists, however, doubt whether such efficiencies could ever be achieved. The second problem is the containment of antimatter. Antimatter annihilates with regular matter on contact, so it would be necessary to prevent contact, for example by producing antimatter in the form of solid charged or magnetized particles, and suspending them using electromagnetic fields in near-perfect vacuum. Another, more hypothetical method is the storage of antiprotons inside fullerenes. The negatively charged antiprotons would repel the electron cloud around the sphere of carbon, so they could not get near enough to the normal protons to annihilate with them. In order to achieve compactness given macroscopic weight, the overall electric charge of the antimatter weapon core would have to be very small compared to the number of particles. For example, it is not feasible to construct a weapon using positrons alone, due to their mutual repulsion. The antimatter weapon core would have to consist primarily of neutral antiparticles. Extremely small amounts of antihydrogen have been produced in laboratories, but containing them is extremely difficult. And even if these proposed experiments were successful, they would only trap several antihydrogen atoms for research purposes. Far too few for weapons or spacecraft propulsion. Heavier antimatter atoms have yet to be produced. The difficulty of preventing accidental detonation of an antimatter weapon may be contrasted with that of a nuclear weapon. Whereas nuclear weapons are fail-safe, antimatter weapons are inherently fail-dangerous. In an antimatter weapon, failure of containment would immediately result in energy release, which would probably further damage the containment system and lead to the release of all of the antimatter material, causing the weapon to explode at some very substantial fraction of its full yield. By contrast, a modern nuclear weapon will explode with a significant yield if and only if the chemical explosive triggers are fired at precisely the right sequence at the right time, and a neutron source is triggered at exactly the right time. In short, an antimatter weapon would have to be actively kept from exploding. A nuclear weapon will not explode unless active measures are taken to make it do so. Cost. A major obstacle is the cost of producing antimatter even in small quantities. As of 2004, the cost of producing 1/millionth of a gram of antimatter was estimated at $60 billion. By way of comparison, the cost of the Manhattan Project to produce the first atomic weapon was estimated at $23 billion at 2007 prices. Smaller one-off assassination weapons are more economically feasible. A modern Mk3 hand grenade contains 227 grams of TNT. 1/billionth of a gram of positrons contains as much energy as 37.8 kilograms of TNT, making the 2004 cost of a positron hand grenade that could be fitted in a sniper's bullet $600,000. This excludes the cost of the micro-containment device, if such a thing is possible. Antimatter catalyzed weapons. Antimatter catalyzed nuclear pulse propulsion proposes the use of antimatter as a trigger to initiate small nuclear explosions. The explosions provide thrust to a spacecraft. The same technology could theoretically be used to make very small and possibly fission-free weapons. Antimatter catalyzed weapons could be more discriminate and result in less long-term contamination than conventional nuclear weapons, and their use might therefore be more politically acceptable. Igniting fusion fuel requires at least a few kilojoules of energy, which corresponds to around 10⁻13 gram of antimatter, or 1011 antihydrogen atoms. Fuel compressed by high explosives could be ignited using around 1018 protons to produce a weapon with a 1 kiloton yield. These quantities are clearly more feasible than those required for pure antimatter weapons. But the technical barriers to producing and storing even small amounts of antimatter remain formidable.